Right. Thank you so much, Dr. Mark Joy Uba. So he's from Northern Illinois University, USA, and title of his talk is Computing Fixed Point of Generalized Non-Expansive Type Maps and Mixed Equilibrium Problems. So Dr. Uba, kindly please start your talk.
Hello, everyone, and thank you to Dr. Miaza for inviting me to this conference. And also thank you for accepting my late submission. So I'll be talking about our paper. So this paper is not yet out. We are just about to revise the paper and resubmit it tomorrow. So I will be presenting the main results from this work. And I will be happy if there are anything that we could catch while I'm making this presentation, that would be awesome. So the thing I'm going to present will be, I'll start with the introduction just to kind of define the basic things we need, and then I will state some results like lemmas we used in the main results. Then I will quickly go over the applications and then show you some reference with respect to this work. Okay, so we're going to talk about generalized mixed equilibrium problem first. So let X be a uniformly convex and uniformly smooth real Banach space, and the dual space would be X star. Then we have this Q to be a non-empty closed and convex subset of this X, such that J of this set is closed and convex. So the J is the normalized duality map. Then we have this duality pairing between X and the dual space. So when we will finish and give application of this result, this duality pairing, I don't know how to point to this. I don't know if anyone is seeing what I'm trying to make reference. Can you see my mouse moving?
Yeah, we can see.
Yes,
We can see.
yes.
Okay, awesome.
Yes.
Okay, so this duality pairing, when we get down to Hilbert space, this is just the regular norm. If we go to sorry, it becomes inner product. Sorry, I missed it. So now let F be a bifunction. So it's just a bifunction that is defined on these two sets. And then we have this phi to be a real valued function. A is nonlinear mapping, any nonlinear mapping. So this equation 1 is what we call the generalized mixed equilibrium problem. So we want to find an element V from this convex set such that this equation 1 is true. This is a very famous equation because it combines variational inequality, equilibrium problem, and optimization problem. So by solving this, we are kind of touching those three problems together in one. So in this work, what we did is to consider a finite family of bifunctions. So our F is not just it's just one function. So we considered a finite family of these functions. So Fi is finite family of bifunctions. So with that, then if we will look at this equation 1 again, so our F here, we are redefining this F in this new work to be this finite sum. So we now, instead of studying what we have here in 1, we are now looking at equation 3. So the generalized mixed equilibrium problem we are solving here will be the one given in 3, not the original one the one given in 1. So here we have like multiple finite family of bifunctions. And the solution set to that equation, the one we studied, will be given by this set. This set given by 4. And we will, as we go down in the slide, we will not make reference to this number 4 again. We just use GMEP to mean generalized mixed equilibrium problem. And then F, A, and this function are those functions we use to define it. So if A is 0, then the problem we are solving will reduce to 5. And this 5 is called the mixed equilibrium problem. And MEP will denote the solution set to this equation number 5. Of course, if F is also 0, like it's identically 0 as well as A, then we are going to be dealing with optimization problem, which is one of the applications of this result. So the class of generalized mixed equilibrium problem is famous, well studied, and they contain special classes, which I already mentioned. So they have so many applications, variational inequality, optimization problems, and equilibrium problem are combined into one problem. So let's look at normalized duality map, the definition of normalized duality map. So this map is a multi-valued map, and it's called normalized duality map, and is given by this equation here. So it is known that if we are in a smooth, strictly convex and reflexive space, then this duality map, it will be single valued and then has also inverse. And inverse of this duality map is defined on the dual space, on the topological dual space of the original space. So in this work, we used J substars. So J star for us in this work is just simply J inverse, but we don't want to be carrying inverse along. We just want to use J star instead of J inverse. So when we see J star, it actually means just J inverse. Okay, and also one more thing is that if X is uniformly smooth, J is also uniformly continuous on bounded sets. Then now we'll get into the most important function in this study, because without this Lyapunov functional, it's difficult to do what we are doing outside the Hilbert space. So let X be a smooth real Banach space. So the only condition we need on the space is that it should be smooth. And then we have this X star to be the dual. This functional is called Lyapunov functional. So this Lyapunov functional is defined by equation 6, where the J we see here is the normalized duality map. So the thing is that if this X, if our set is Hilbert, so if we are in a real Hilbert space, this equation 6 will simply reduce to norm square. So outside Hilbert space, it means this 6. But when we are in Hilbert space, then it will reduce to just norm squared of X minus Y. So from this definition, we see that this function is never going to be negative. So it's not negative. It's not negative by the way it is defined by this property number 7. So it is bounded above and below by non-negative values. Now, let's talk about non-expansive, because we are going to be looking at generalized non-expansive maps. So when we have two spaces, X and Y, that are just normed linear space, that's the only condition, normed linear space. So we say that a function will be non-expansive if one of these two conditions happen. So I use this diagram to show what we mean by non-expansive. So in the first diagram, you will see that the distance between Tx and Ty is smaller than the distance between X and Y. And that is what is given here on this line here. You see this the distance, the norm, right, is less than this norm in the two spaces. Then the next one is in a situation where they're equal because we have less or equal. So one of the two could happen. So this is what we mean by non-expansive maps. Now, the next thing is to look at what is called generalized non-expansive map. I think this was introduced by Takahashi and his group. So let this gamma be a non-empty closed and convex subset of a real Banach space, and T be a map from this set from this convex set to the original to the main space. So this map T will be called generalized non-expansive if, first of all, the set of this fixed point set will not be empty, will be non-empty, and that's Lyapunov functional. So if we use Lyapunov functional instead of the norm, if we go back here, we will see that the regular non-expansive says the norm in Y is less or equal to norm in X. But when we go out, so if we are in just any arbitrary norm space, then to study this generalized one, instead of using that norm, we are using this Lyapunov functional. So we have phi of Tx comma P less or equal to this. So this is what we called generalized non-expansive map. Then the next thing is to talk about retraction, because we will again be using this to describe our results down the line. So a map R from the original space onto this convex set will be said to be a retraction if this composition will give us R itself. So if R composed by R is going to give us R, then we say that this map is a retraction. Then the map will be said to be sunny if we have that R of this combination will give us R of X for all the X in this space, and then T is positive. So if we have this, we say that the map is sunny. Now, the last thing here will be sunny generalized non-expansive retract of X. So an non-empty set, if we have this same gamma to be a smooth Banach space, convex subset of a smooth Banach space. So this is said to be sunny generalized non-expansive retract of X if there exists a sunny generalized non-expansive retraction, that is the map from X onto the convex set. So if that happens, then we will say that this set is sunny generalized non-expansive retract of X. Then the next thing is what is called the NST condition. So again, we have this closed subset of a Banach space. So if we have this family of Tn's, and then we have this set also, gamma, if there are two families of generalized non-expansive maps of this convex set into X, such that this countable intersection is not empty, and this is true, then this is what we call the non-ST condition. We say that a sequence Tn will satisfy this NST condition with this set if for each bounded sequence, if we pick a bounded sequence, and then we'll take the difference between this bounded sequence and Tn of that bounded sequence. So if the norm goes to 0, if it implies that also that this limit is 0 for all T, then we say that that sequence Tn satisfies the NST condition. So now the notation we're going to use, I already mentioned this before, that here this X star will just be the dual space, so the space of bounded linear functionals defined on X. and the J will be the normalized duality map. This J star, J sub star, is actually the normalized duality map defined on this duality space, dual space of X. But we have already said that our J inverse is exactly J star. So the original J, the original duality map goes from X to X star. So the inverse will go from X star to X. So that's what we mean by this. And this is what we're going to use all through. Okay. A map is said to be J closed. So if we have a map T from a convex a set to the dual space, this will be called J closed, J star closed. If we compose the inverse of this this duality map with T, it happens that will give us a closed map, the regular closed map we know. So that is if we have a sequence in this set such that it converges to this, then if we compose T with this inverse, then it should go to Y, and then this will be true. So this is what we mean by J closed maps, J star closed maps. Now we get to what is called J fixed point. So this J fixed point has different authors call it different things, right? So I think the first time it appeared, it was called semi-fixed point. And then at a different time, later on down the line, it was called duality fixed point. And then subsequently around 2016, then it was called J fixed point. So in this study, we are going to stick to J fixed point. We're going to use J fixed point because that's the most recent nomenclature for this. So a point will be called a J fixed point of T if T of X will give us the same as J of X. So J is the duality map. So these two things are all in dual space of our original space. So the set of J fixed point of T, we will denote it by Fj of T. The regular fixed point set, we use just F of T. But for this J fixed point, we will use F sub J to mean that we are making reference to duality fixed points. Now, a map T from this convex set to X star will be called generalized J star non-expansive if it happens that the J fixed point set is not empty, and then we have this Lyapunov functional of P with this map less or equal to Px for all X in the set, and then for all P in the J fixed point set. So if this equation is true, then we say that we have the map is J star non-expansive. Now we have also what is called generalized J non-expansive, and that is given. So when we switch, this Lyapunov functional is not symmetric. So if you have phi of xy, it's not necessarily equal to phi of x yx. So it's not symmetric. So some authors defined we have this generalized J star non-expansive maps, which is given by, in this definition, the first component of this map, the first input here is P. For the J non-expansive, the second input is P. So if you flip the order, then for generalized J star non-expansive, we have this, and then for the J non-expansive, we have the other version. Just if you switch it, you get one of them. So the good news is that when we will go down to Hilbert spaces, they are the same. This generalized J star non-expansive and J non-expansive, they are the same in Hilbert space. They agree in Hilbert space. Okay, so now we have this condition which we called A to 4. This again is classic in this kind of research. This is not part of our result. It's not like we have this is known is well known in literature. So we call it conditions A to 4. So f of x star is 0 for all x star in J. F is monotone. meaning that this is true. And then, so we have these conditions. We call it A1 to 4 condition. This we will use in the main result. Now, one more lemma we use before we get into our main result is that if we have this set gamma to be non-empty closed and convex subset, and then the following will be the same. So if we have that J of this set is closed and convex, then it means that the convex set itself, this gamma is generalized on expansive retract of X. It also means that it's a Sunny generalized on expansive retract. So anyone you get, the other one follows. So we need this in the result. Okay, so this is the main result. So this was submitted to fixed point theory last year. And just recently, it was recommended for publication. So we just need to review it and then revise it and then send back to them. So this is what we have as the main result. So we say let X be uniformly smooth and uniformly convex real Banach space with the dual space X star. Then we have our gamma to be non-empty, closed, and convex subset as well. So if we have our phi to be lower, semi-continuous, and convex, and then our bifunctions will satisfy those conditions 8 to 4. So to be the F star will be equal to 0, F will be monotone, and then the rest, these other two ones. So if all those, for each I, if F is a bifunction that will satisfy those conditions, then our T, our families of, so this is countable family of J star non-expansive type maps. So if all these assumptions are true, if we assume that J of the fixed point set is convex, and also that this T satisfies the NST condition with this gamma, then we have this algorithm given by 8. So this algorithm will convert strongly to this point where RB is the Sunny generalized J star on expansive retract of X onto B. So this is the main result. This is for generalized J star on expansive. So this is the first thing we proved, that given all those conditions I gave in the previous slide, that this scheme, this equation given by 8, will converge to this retract. Then the next theorem handles the other version. So when we will switch so here
Dr.
we
Uba,
did
you have 2 minutes.
Oh yeah, so I'm almost done. So we have J star on expansive for 3.1, and we have the scheme. So for 3.2, we studied J non-expansive maps, and we have that this scheme generated by given this scheme, this sequence here, we converge also strongly to this. Then the corollary is that because in each of these, we looked at generalized mixed equilibrium problem. So for the corollary, we have that if A is identically 0 in those two theorems, then all those two results we have will also be applicable, will be true also for mixed equilibrium problem. And this will converge also strongly to, just like we did in the original theorem. So for applications, we were able to show that these 3.1 and 2 are applicable in classical Banach spaces. Of course, that is true because since we proved it in a more larger space, in particular, it is true in all these spaces as well. And then when we go to Hilbert space, so for the Hilbert space case, the phi, that Lyapunov functional changes to norm. So now instead of using norm, every single thing we have is still true, but this time we will be using norm instead of the Lyapunov functional. And our retract, the retract we studied in the original case becomes metric projection. and these are the references. So this is the work we published in 2021. We began this work like over 5 years ago, and then the most recent one is this one I just presented now. And thank you for your attention.
Right. Thank you, Dr. Uba. Let us thank our speaker.
Thank you so much for the nice presentation.